This is lessons 9 and 10 on scientific notations and the operations we can do with scientific notations like addition, subtraction, multiplication, division, and I'll be showing you examples of all of those. But we need to start with the basics of scientific notation. So first I'm going to show you how to just manipulate numbers by multiplying them by powers of 10. So I want to change all of these numbers into 234.567. Okay? So on this first one, we have a decimal right after the 2. But I don't want the decimal to be right after the 2. I want my first number to show 234.567. So I need to be thinking, I need to move this twice. I need to make this number appear 2 decimal places bigger than it actually is. In math, you can do that. The problem is you always need to keep things balanced. So if I'm making something bigger by 2 decimal places, I have to essentially make something else smaller by 2 decimal places. And the way that works is we know that when you multiply something by 10, you're actually moving it up a decimal place. Like 3 times 10 equals 30. That 3 is moved up a decimal place. So here I've made something bigger by 2 decimal places, so I need to make this smaller by 2 decimal places. So this is going to be a -2. So I can rewrite this number to be 234.567 times 10 to a -2, and this actually equals the original number that was there. Let's try the next one. We have 234.567. Oh, well here, that's actually the number we want. So we don't need to move that decimal at all. That decimal's happy right there. So what kind of power of 10 can I multiply by that it won't move? You're thinking 10 to 1 moves it one place, 10 to a -1 moves it one place. 10 to the 0, though, won't move it at all because 10 to the 0 is just 1, and you can multiply any number by 1 and it doesn't change it. So we can actually just keep this and just put it times 10 to a 0 because it's not going to change it at all. And I won't rewrite that one because it's already pretty clear here. Let's take a look at this next one. I have the decimal right in front of the 2, but I want it right after the 4. So I need to make this number bigger by 3 decimal places, so I need to make something else smaller by 3 decimal places. So to rewrite this number, so I have 234 as that first number, 234.567 times 10 to a -3 is this exact same number that we started with. All right, taking a look over here. Here we have a nice whole number, and all whole numbers actually have a decimal at the very end. We don't typically write it just because it's in bad form. You don't need to put it there. We all recognize that it's there. But there is one right at the end, and we need to be thinking, I want to move it 3 spots forward, 3 spots to the left, which means I'm actually making this number smaller by 3 decimal places. And if I'm making something 3 decimal places smaller, I need to make the 10 bigger, so it's going to be a +3. So if I rewrite this one, and I'm going to do it in the middle because I have room, but you can write it wherever, 234.567 times 10 to a +3, because this essentially means that this number actually isn't this small. It's actually 3 decimal places bigger. Okay? That's all that we're representing. The powers of 10 are showing that this isn't actually what the number means. It's actually 3 times bigger, 2 decimal places smaller, 3 decimal places smaller. So let's take a look at the next one. We have a decimal place in between the 3 and the 4, but we want it between the 4 and the 5. We need to move it just 1. And we're making this number bigger by 1 decimal place, so we need to make something smaller by 1 decimal place. So this number becomes 234.567 times 10 to a -1. And that times 10 to a -1 is saying this number is not how it appears. It's actually 1 decimal place lower. Okay? What about this one down here? This is a nice whole number again, so which means there's always a decimal right at the end. Well, how many decimal places do we need to move it? We want to get it right here, so let's count. 1, 2, 3, 4, 5. That needs to move 5 decimal places. Now, Are we making this bigger or smaller? We're making it a lot smaller. So if we're making something smaller by 5 decimal places, we need to make something bigger by 5 decimal places. So let's rewrite this one. We have 234.567 times 10 to a positive 5. And again, what this 10 to a power of 5 means is this number is not as small as it appears. It's actually 5 decimal places bigger. Okay, so you could always expand it back out to here. You could expand any of these back out to the original number. That power of 10 is almost just like a space holder. So it's like, hey, no, that decimal wasn't actually here. It was 5 decimal places over. Or it was 1 decimal place over. Okay, and that negative positive tells you which way that decimal really should be. Okay? So let's get down a definition for scientific notation. Scientific notation is just a way for scientists and mathematicians to use really, really small or big numbers without it being a pain. Okay? So there's always a standard form that it's in. And it's actually always 1 digit to the left of the decimal times a power of 10. And you are probably thinking, none of these are like that, and you're absolutely right. Okay? So realistically, if we wanted a scientific notation, we should have 1 digit to the left of the decimal times some power of 10. So some power there would be our scientific notation. And we could change all of these. So now let's practice turning some numbers into scientific notation now that we know what that is. So on our sheet, we have this first number. We have a decimal, 2 zeros, and then a 364. Now remember, scientific notation says that we need 1 number past the decimal, and that number can't be 0. Okay? So what we're going to do is we're going to take this first number, this 3, and that'll be our first number to the left of the decimal. Okay? Now, we still need to attach that 6 and that 7. That's 4. So let's attach the 6 and the 4. So we're going to change this number into 3.64. Then you're thinking, okay, next part of scientific notation is times some power of 10. And you're right. Now, thinking back to the activity we just did, we have to keep these balanced. So I need to be thinking that the decimal was here, but I actually moved it 3 spots to be right behind the 3. And I made this number bigger by 3 spots. Well, if I made this number bigger by 3, I need to make the 10 smaller by 3. So I'm going to put a -3 there. And that's how you change things to scientific notation. So this number in scientific notation represents this original number. It's saying 3.64, yeah, those are the numbers involved, the actual digits, but where that decimal is actually 3 digits away. It's actually 3 digits smaller. All right, let's go down below. Whew. You can see that, yes, this would be a number that's not very nice to work with. For most of you, probably wouldn't even fit into your calculator. So let's change it to scientific notation. I need 1 number out front, so that's going to be our first digit. That 8, because it can't be a 0 out front. We need to tag along everything else. So 8's our number to the left of the decimal, and then you just tag on everything else in order. Then we need it times 10 to some power, and then we can find out what power that is. I need to move this decimal to be here, so it represents exactly what's here. So let's see how many times we move it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I made this number bigger by 10 decimal places, so I need to make this smaller by 10. So I'm going to put a -10. So hopefully you're recognizing that the negative numbers are showing that this number is actually a lot smaller than it appears. Same thing here. I have a negative, and so the bigger the negative is, the more smaller this actually is. That's probably bad grammar. The smaller this number actually is because this negative is so negative. I need to move that decimal 10 places, making this smaller to actually represent this real number. Okay. So now let's take a look at some bigger numbers. 130,000. So we need some number before the decimal. So we'll just take our first actual number, because it can't be a 0. So we'll take our 1, put a decimal, and then carry out everything else. Normally we don't tack on the zeros, okay? Because on decimals, technically there's an infinite amount of zeros after them, and it's really bad form to write those. So we're just going to leave this as 1.3, okay? If you tack on the zeros on your test, I won't mark it down. It's just not good form. So we have 1.3. We have one decimal to the left, or sorry, one number to the left of the decimal. We need times some power of 10. So let's find out how much we need to move this decimal. So this is a whole number, so all whole numbers have that decimal right at the end, and we need to move it to be right next to the 1. So let's see how much we move it. 1, 2, 3, 4, 5. I moved it 5, and I made this smaller by 5 decimal places. So I need to make this bigger by 5. So remember that 10 to the 5th power is saying this 1.3 isn't so small. It's not actually 1.3. It's actually a lot bigger than it appears. Let's take a look at this next one. This one's not so happy looking because it doesn't have as many zeros, but it will still work out. So we need to take our first actual number, that 1, keep it to the left of the decimal, then everything else can be carried behind. Now we need it times 10 to some power. So let's see what that power is. This is a whole number, which means there's a decimal right at the end that we don't actually see, but we can write it in for now. And we need to move it to here. So let's see how many times we move it. 1, 2, 3, 4, 5, 6 places. We're making this number 6 places smaller. So I need to make this 6 bigger. So it's going to be a positive 6. So hopefully you notice now that in dealing with big numbers, you're going to have a positive exponent because we're actually saying these numbers are bigger than they appear. So let's write down our rules, all these words that are underneath. If you are making the number bigger, like here, we made the number bigger, you need to make the exponent smaller or negative. So if we're making the number bigger, just like here, we made the number bigger, we're going to need to make the exponent smaller, or you can think of it as making it negative. Next thing, if you are making the number smaller, like we were there, because it's not 130,000, we changed it to 1.3, so we made it smaller, you need to make the exponent bigger to counteract it, or positive. We can also think about it in a different way, and I apologize if there really isn't room for this on your sheet, but you can scribble it in elsewhere. I'll just put it right underneath. Negative exponents represent small numbers. Just like here, this negative exponent actually represents that this number is much smaller than it appears. Same thing here, this number is actually much smaller than it appears. Whereas positive exponents represent big numbers. Just like over here, this 1.3 is not just 1.3 because this positive 5 exponent says that this 1.3 is actually much bigger than it appears. Same thing down here. This 10 to the 6th power says that, hey, this number's actually bigger than this little decimal that's right here. All right, now let's take a look at going the other way, being given scientific notation and expanding it back out to its true number. Okay, so we have 1.837 times 10 to a negative 4. So we have to remember that negative 4 means that this number is actually smaller than it appears. It's actually 4 decimal places smaller. So sometimes this will help you, is to add just extra zeros. So first, let's decide which way we're moving the decimal. So you should be thinking, well, I'm going smaller. So if I go this way, the number's getting bigger. So I need to go to the left. I need to move this decimal places 4 places to the left. So let's add some zeros on this tail end. So I need to be thinking that I'm going to move it from here over 4 times. 1, 2, 3, 4 to right there. So we need to move that decimal place 4 times over to the left to make this number the original small number that it was. So let's rewrite this. We always have a 0 in front because otherwise it's actually improper to write. We have 3 zeros, then our 1, 8, 3, 7. Now, how do we know that we're right? How do we know that this was actually the way that this ended up? Well, we can just count it out again. If we moved it into scientific notation again, moving this decimal to be right here, then we would have made it smaller by 4 decimal places. Or sorry, we would have made it bigger by 4 decimal places, so we would have had to have a small 4 here, a negative 4 here. So yeah, it's correct. Let's try this next one. We have a 9.83 times 10 to a 0. Well, that 10 to the 0 says that it moved nowhere. It didn't move at all. 10 to the 0 is 1. So this number actually is still 9.83. That is the original number. Just they put it into scientific notation that way. Let's try over here. We have a 2.8 times 10 to a 5. That 10 to a 5 says that this number is actually bigger by 5 decimal places. And I'm sorry that there isn't really room, but you might want to write it right above, 2.8, and then add on some extra decimals because we need to make this number bigger going this way. So we need to shift everything that way. So we need to make it bigger 5 decimal places. So let's move it 5 decimal places. 1, 2, 3, 4, 5. So it's going to stop right there. So let's write what that number is. 28 and then 4 zeros. So it's actually 280,000. How can we check that we're correct? Well, let's change that back to scientific notation. If I wanted to change this to scientific notation, I start right at the end because that's where my decimal is, and then move it to right behind the 2. That's 1, 2, 3, 4, 5 spots, making it smaller, so I need a positive 5 as my power. Now looking at the very last one, we have, yeah, a pretty nasty decimal, but that doesn't really matter. What matters is this power. This power says that it's bigger by 2 decimal places. So let's make it bigger by 2 decimal places. If I'm making it bigger, I need to move this way. Okay? I don't want to make a bigger decimal. That'll actually making it smaller. So I want to make it bigger going this way. So the decimal's here, and I move it 1, 2. So that just becomes 629 point, then the rest of that junk. So how do we check that we're correct? Well, just go backwards again. Decimal's here. Scientific notation needs to move it here. So I move it 2, making it smaller by 2, which means the exponent needs to be bigger, a positive 2. Okay, now let's look at an example when we need to subtract scientific notation. So take a look at the problem. Find the difference in the populations of Texas and North Dakota. So already off the bat, you're saying, okay, what am I doing with these? Even if I hadn't told you that we're subtracting, this word here, difference, tells you that we're subtracting because difference is the end result of subtraction. So if you really even need to, if you want to, you could just write in subtraction. Might be a good practice for you to do every single time you see that word to write in, oh, I'm doing subtraction. In the same way that if you see product, you know it's multiplication, quotient is division, and all of that. So finding the difference, so we're going to have to do subtraction. Finding the difference of the populations of Texas and North Dakota. Texas has about 26 million people, and North Dakota has 6.9 times 10 to a 4. So here we're given the information in 2 different ways. So I'm going to show you the answer in 2 different ways. So let's do it the long way, as if we didn't know scientific notation. So Texas has 26 million. So let's write out that number. 26, and that's million. North Dakota has 6 times 9 to a power of 10. Now we just learned how to expand that out, so we need to do that. It's a 6 and a 9 And then we need to make it bigger by 4 spots. So it was here. So there's 1, 2, 3, 4. Let's check that we did it right. It was here, and it goes 1, 2, 3, 4 to make it bigger by 4 decimals. So wow, that's a really big difference between Texas and North Dakota. So what's the difference between Texas and North Dakota? Well, we just need to plug it into our calculator. Hopefully our calculator does this. So we need to subtract 26 million. We need to subtract, the 69,000 from the 26 million. Now you can go through and do it the long way, the whole borrowing. I'm going to cheat and use my calculator. All right, cheating. 26 million minus 69,000 equals out to be 25931,000. So the difference is 25,931,000 approximately. Now, if I didn't have my calculator with me, that would have been some really ugly, long subtraction. So that's why I'm going to show you the scientific notation way, because it works even without having your calculator around. So obviously, if this is the scientific notation way, I probably need both numbers in scientific notation. So let's change Texas. Texas is 26 million. 26 million. Now the decimal is right here. I need to move it to here because I need to be 2.6 times 10 to some power. So let's count up what that power is going to be. 1, 2, 3, 4, 5, 6, 7. Because I need to represent the fact that this number is actually 7 decimal places bigger in reality. So I just changed the population of Texas to be 2.6 times 10 to a 7. And I don't need to change North Dakota because they were nice enough to give it to us like that. North Dakota, 6.9 times 10 to a power of 4. We can't just subtract these the way they are right now. There's actually something we need to do first. We need to change it so both of them have the same power of 10. And luckily, we know how to do that because we know how to manipulate numbers. So the easier way, I'm going to say, is to change this one, to change Texas. Instead of making this a smaller number, we can just make this a bigger number. So let's change Texas. And hopefully this is still on the screen. To have a power of 4. So we need to change Texas to have a power of 4. So it's going to be the same power as North Dakota. I need to change it bigger by 3, because if I'm making this smaller by 3, I need to change this number bigger by 3. So it's going to look like that. And notice I only moved it 3 times. So it was here, it went 1, 2, 3. Okay? So again, since I made 7 into 4, which is 3 smaller, I had to make our initial number 3 bigger. And we'll keep North Dakota the way it is. Now, let's write it out. We have 2,600 times 10 to a 4th minus 6.9 times 10 to the 4th power. What we can do here, and this is kind of the opposite of distribution, you're undistributing things, is we can essentially take out the powers of 10 because they're the same. So if we take it out from both of them, it doesn't actually go away. We're just going to undistribute it. It leaves behind our numbers. So we have 26,000 and our 6.3. Okay? Now we can actually just do these numbers. So now instead of doing the whole multiplication of 26 million and 69,000, we only need to subtract 2,006. Okay? So I'm still going to cheat and use my calculator, but again, the long way of doing this would be much simpler. So that ends up being 2593.1 times 10 to a 4. Okay? And take a look. That's the same thing we got over there. Now, we should leave this in scientific notation. So on a test, if it asks you to do this. You could do it the long way and then change this to scientific notation. So let's take a second and do that just so we can check it with our other answer. So we would have 2 as our front number with a decimal afterwards, all the other significant numbers afterwards, so the 5, the 9, the 3, the 1, times 10. And then we need to decide what that exponent is. So it goes 1, 2, 3, 4, 5, 6, 7. It gets smaller by 7, so this is a positive 7. So let's check if that's the same thing we get over here. This is close to scientific notation, but it's not because we need the decimal to be here. So we need to be 2.5931. So how many times do we need to move it? We need to make it smaller by 1, 2, 3. So we need to add 3 to this 4, so we get to 7 again. Oh, those are the same. For really, really big or really, really small numbers, this method is actually much easier. I know that right now this looks easier and it's the way that we're familiar with, and if you have a calculator, it's nice. But again, if you're going to do really big or really small numbers, a calculator can't even help you there. But either way, you get the same answer. Okay? And always pay attention from now on if the answer should be in scientific notation, in which case getting something like this or getting something like this would only get you a 3. Now, I'm actually not going to be showing you an example of addition right now, but it's the exact same thing. It's just instead of subtraction,